Hello, this is Mr. Ferris. Today's lesson is on graphs of exponential functions. And you will need your graphing calculator. We'll do quite a few things with your graphing calculator, so make sure you have that available as we go through this lesson. First of all, we're going to examine the behavior of several different kinds of exponential graphs, hopefully very quickly using some cool technology called Desmos. I believe some of you uploaded that app on your iPads, and so that would be a good one to have available to you. You can also go to desmos.com, D-E-S-M-O-S, and you can find that same graphing calculator. So exponential functions, as we know, have this particular form. Some quantity is equal to a times b to a variable power. And so we're going to look very closely at the graphs of several different kinds of exponential functions, and we will look particularly at what a does and what b does when you change the values. So I have a exponential function, just a generic one. Notice in Desmos you can graph a function that is a times b to the x, and then you can set up sliders where then you can change the value of a or b or both, and then you can watch in real time what that does to our graph. So I hope this looks familiar. This is a pretty generic exponential function. It's growing at a rate of 2 per x, so it's doubling for every 1x. And it looks something like this. It's an increasing exponential function. It's concave up. And first of all, why don't we just move a around a little bit. You'll notice that if you drag a and make it bigger, then of course the y-intercept gets bigger and bigger. And we can verify that by actually clicking on here and have it give us this point value. And you'll notice that that matches up. If a is 1.9, then the y-intercept is 1.9. And if we drag it a little bit bigger, if a is 2.4, you'll notice that the y-intercept is 2.4. So I believe it's pretty safe to say that the y-intercept value on a graph will always be the a number in the exponential function. So let me put that back a little bit lower here, and we'll see what b does. If you play with b, b is the growth factor. b is the number that we're multiplying by for every x. And as you might imagine, as you increase b, this graph gets steeper. In other words, it is growing at a much faster rate, so therefore it's going to become closer to vertical. And as you go lower and approach 1, something kind of weird happens when you get right on 1. If the growth factor is 1, of course, it's not growing or decaying. In fact, if I got it right on 1 exactly, you would find that it's a horizontal line. It's not even really an exponential function at this point. And then as you go a little bit less than 1, you'll notice that the exponential function has a completely different look to it. It is now a decreasing exponential function. And I hope that makes sense, because now you're multiplying every time by something less than 1. And if you continue to multiply any quantity by a number less than 1, why then it will get smaller and smaller and smaller. And so we can make the growth factor go further down, further down, further down. And of course what happens is it decays faster. In fact, I can get it all the way down to 0.01. It's decreasing very, very fast, which means it's coming down almost vertical, very steep, and it approaches 0 very, very quickly. And so there you have some of the behaviors of a and b. And so let's summarize. First of all, a always represents the y-intercept on a graph. That's what we discovered. No matter what type of exponential function we were looking at, the coefficient a is always going to be the y-intercept on a graph. Now, if this was a story of some sort or an application, then it might refer to the initial amount or the starting amount. But on a graph, when we look at the graph of the function, it will always be the y-intercept. And then b, the coefficient b, is always going to stand for the growth factor. We know that from previous lessons, but as far as the graph goes, b represents the steepness and the direction. And so we find that b is a little more complicated. So one of the things we find out is that if our growth factor is greater than 1, then the graph increases. Then it's an increasing function. And if b is between 0 and 1, then it decreases as you go left to right, of course. So that's one of the things we found out, that the key number is 1. When you're above 1, it's an increasing exponential function. And when you're between 0 and 1, then it's a decreasing exponential function. So just a little kind of just a little icon here. That's what it looks like if it's an increasing exponential function. This is what it looks like when it's a decreasing exponential function. So B has a couple ranges that or domains, I guess you could say. It has some intervals over which we want to make sure we know exactly what the function is doing. And in both cases, of course, they are still concave up. All right, now you may have noticed that both exponential functions that we just looked at, the ones that were increasing and the ones that were decreasing, also have a common feature. They were both concave up, but there was another feature that if you would graph several of them at the same time on the same graph, there's another feature of all exponential functions, at least the ones that we commonly will be looking at, and that is happening right down here. You might notice that no matter whether it's an increasing exponential function like these two are, or whether they're decreasing exponential functions like these two are, all four of these are approaching, you might see, are approaching the x-axis. And so the x-axis, or we could call that the line y equals 0, is a horizontal asymptote. So for the exponential functions that we will be dealing with, pretty much all of them, the regular ones, we'll have y equals 0 as a horizontal asymptote. In other words, kind of the fancy way to say it is that our function will be approaching, that's what we use for the symbol for approaching. The function is approaching 0 as x approaches infinity. That would be what's going on as we travel this direction. So as our x values are approaching infinity, as x gets bigger and bigger, the function is approaching 0. On the other side, as we look at the decreasing functions, now we have to kind of think a little differently because this is not the normal way we travel or we analyze functions. But if x were to travel in this direction, notice that the output values would again be heading towards 0, be heading toward the x-axis. So kind of for the other kinds of functions, for decreasing functions, the function will be heading towards 0 as x approaches negative infinity. So for decreasing functions, it's true that the function heads towards 0 as x approaches a big number positively. And as we analyze the kind of the red function, if x were to travel toward negative infinity, we would see that the function is heading towards 0 in that direction. So once again, it just shows in fancier language, this is kind of the fancier language, is saying the same thing, that y equals 0 is a horizontal asymptote. Now we want to look at some practice at some calculation type problems. So here's a table of values. You have t, which might be time, I suppose, could be time, and we have a function. The first question, of course, would be whether this is a linear function or an exponential function. So one of the nice things about this particular one is it's set up a little bit easier because notice that t is going up by 3, up by 3, up by 3, up by 3. So we know that delta t is constant. So now it's a little bit easier to see what's going on with the function because we don't have to worry about t. We know t is going up at regular intervals. So now we want to check linear. Linearness, of course, is a constant rate of change. So this is going up by, looks like 94. But this is going up by over 100. This is going up by several hundred. And this is going up by 560. So clearly, we're not having a constant rate of change. So no, it's not linear. But now that doesn't mean that it is exponential necessarily. All that means for sure is that it's not linear. So again, we know that the difference in the t's is always 3. But now to check exponential, we don't do differences anymore. We want to find what the common ratio is. And to find that, the common ratio is more easily computed by taking the 216 divided by 120. In other words, you take the second output divided by the first output, and that will give you a ratio, and that ratio turns out to be about 1.8, I believe. If you take the ratio of 389 to 216 to check that ratio, turns out it's 1.8 or very, very close. I think it might not be exactly. If you take 700 divided by 389, that'll be close to 1.8. You take these two numbers, that'll be close to 1.8. And I say close because it's very difficult to get whole numbers like this to be exactly the same ratio. And then also, these numbers very well may be data from some sort of a experiment or something. And quite often, data will not be perfectly linear or perfectly exponential. But as long as these ratios are awfully close to 1.8, I think we can safely say that we have an exponential function here. So yes, we know there's an exponential function. Our reasoning would be something like this. We have the same ratio. Every time we checked it, the ratio is 1.8 for every difference of t of 3. Now, I say it that way because of our next question. The next question is, what's the growth factor? 1.8 is not the growth factor. 1.8 just allowed us to check to make sure this was exponential. We have the same ratio for the same interval of t. But remember, the growth factor is what you multiply it by every time t increases by 1. So the growth factor is for when delta x is 1, and we don't have that number yet. All we know is that when delta x is 3, or delta t is 3, we know it increases times 1.8. So now we've got another little problem to solve here. How do you find the growth factor when every 3 increase gives you a factor of 1.8? Well, if we think it through, it's kind of like, in fact, here's probably what I would do. Let's just take these two ordered pairs in green right here. Just those two ordered pairs. We can make an argument that we're starting at 120 and we're ending at 216, and we know we're doing it exponentially, and it takes 3, we could call that years to do that. So let me just think this through as if it's an exponential function. Exponential functions, you remember, are y equals a times b to the t. And we just said that we're starting at 120 and we're growing it to 216 exponentially. The only thing is, we don't really know what the growth factor is, but we do know it takes 3 years to do that. So if we just write a little exponential function, just a little quick one here, and just pretend that 120 is our starting amount, 216s are ending amount, and it takes us 3 years to do that, why, we've got a little equation we can solve very quickly. You just divide both sides by 120, and we get about 1.8, of course. We did that earlier. And 1.8 equals b cubed, and then all you got to do is take the cube root of both sides, and you will find the growth factor. And it turns out that the growth factor, I believe, is 1.216 if we go out to 3 digits of accuracy. So 1.216 is the growth factor for this table. All right, I kind of erased everything because it was getting a little clogged up. You can always rewind and pick up on the work there if it went a little fast. All right, so the formula then is going to be h of t equals, we don't know a yet, but we know the growth factor. We just figured out it's 1.216 to the t. So how do we find a? Well, we've got quite a few ordered pairs we can choose from, so we could just temporarily plug in one of the ordered pairs of our choice and do a little algebra. Now we want to find what 120 is. We can do that by dividing both sides by 1.216 to the 9th power. That'll give us a. And it turns out a is about 20.64, I believe, something like that. 20.64. So our final answer, the final formula then, if I put all that together, the formula for this will be h of t equals My initial amount was 20.64 times 1.216 to the t power. There's the formula for this table. Now we're ready to answer a couple more questions. When would this formula, or when would this function h hit 1,000? When would h at t ever be 1,000? All right, so let's go back. Our formula was h at t equals 20.64 times 1.216 to the t. And we want to know when this equals 1,000. So how would we solve that? Well, if you happen to remember logarithms from last year, you could do it algebraically using some properties of logarithms. But since we're not really there yet, we have another method that we can employ to solve this, and we're going to use our graphing calculators. And so what we will do, one method of doing this is to type this into y1 and then type this into y2. And what you're going to see is, of course, you have an exponential function. So when you graph the exponential function, it's a growing exponential function, so it's going to do something like this. And then when you graph 1,000, y equals 1,000, that's just going to be a horizontal line. And your idea then is, a way to solve this is if we could just find when they intersect, then we will know what t is. We're solving for t, remember, and t is time, t is this axis. So if we can figure out where these two graphs intersect, then we will have the time that solves this equation. So this is the graphical method of solving for an output of 1,000 for any function, but we're going to do it for exponential functions. So get out your graphing calculator. So first of all, you need to go to y equal to, top left corner, and type in the two functions that you just saw on the screen. One of them goes into y1, the other one goes into y2. Now, assuming you have that in there, of course, the next decision is how in the world do we get a window so we can see this? And I hope you know that since y2 is 1,000, that's going to need better than just zoom 6. So if we know it's going to be at least 1,000, that's the horizontal line, then probably our window needs to go at least to maybe 1,200 on the y max, something like that. And then we also can tell from what we just learned that 20 is going to be the y-intercept of the exponential graph, and it is going to grow at a factor of 1.2. So you put that all together, we don't really know what x is going to be. So let me just give you the window this time and just know that some of it requires some guessing and checking if you don't know for sure. And you just have to be persistent. But this window will work nicely. So if you go negative 10 on the x min, 25 on the x max, negative 10 on the y min, and 1200 on the y max, that should give you a nice window where you can see both equations. So if you go to the graph button, sure enough, there they are. The exponential function does hit the y equals 1,000 horizontal line. And now our job will be to find the intersection of these two equations. Well, it turns out in the calculate window, which is second trace, one of those options that we've been looking at before, we've looked at zeros and maximums. Number 5 is the intersect calculation. This will find the intersection of any two functions that you have typed into your calculator. So if you select number 5, you'll be asked 3 questions, but this time it's not left boundary, right boundary and guess, but it's first curve, second curve guess. So the question is first curve. Well, if you go to the top of your screen, you'll see it's suggesting that maybe y1 perhaps is your first curve, and if that's yes, why you just hit enter. If it's not, you can use your up and down arrows to navigate to the correct equation. But that is our first equation, so we'll just say yes, or we'll say enter. And then we'll ask, is the second curve this equation, y2 equals 1,000? And yes, it is. It's even blinking at us there. And you say enter, and then you're supposed to guess. In this particular case, there's really only one intersection, and so a guess is really not necessary. If you had graphs that intersected 3 or 4 places, you would have to tell the calculator which one to look at. But I will just say enter because I'm pretty sure that's the only intersection in the neighborhood, and there it is. So apparently, This intersection occurs when time, or t, is 19.8. 19.8 is the time at which, clearly you can see here that the graph hits 1,000. So that would be our answer to the equation. So t would be 19.8. So our final answer, when would t equal 1,000? We graphed this, something like this. We had an exponential function, then we graphed y equals 1,000, and we found out that this point right here happens to be at about 19.8. And whatever the time is, it would be seconds or years or something like that. We don't really have a story, we're just doing the mechanics here. So that's one question down the road, and then the final question is, where's the asymptote? Well, because this is kind of a normal exponential function, the asymptote would be the x-axis. But remember, this is a particular kind of exponential function. This exponential function approaches the x-axis kind of in this direction. So the way we write that has to be pretty precise. Our x, if you travel like I did with the blue dot there, our x was heading toward negative infinity. So the way we would want to write this in fancy notation is our function, which I realized I just wrote the wrong one, so I'll go back to h at t. Our function h at t is heading towards 0 as x heads toward negative infinity. That's the way we had to kind of think it. Our x value, as we went this direction, was heading toward negative infinity, and then the h value was heading towards 0. So this would be the asymptote statement written in its fancy form. In layman's terms, we could just say it's heading toward the x-axis as you travel to the left. That would be kind of the common way to say it. All right, a couple other examples. I'll try to go through these quickly, but also with enough detail that you get the idea. Here we have an example of a capacitor, which is something in a component like a stereo or a speaker, some sort of electrical component. A capacitor holds charges, holds electrical charge. And so you may notice sometimes when you turn off a stereo, it doesn't go off instantly. It kind of fades out. That's the capacitor decreasing its stored charge. And so it says that this particular example will, or whatever the capacitor is for this particular problem, is going to lose charge exponentially with this particular function. And so a couple of the questions that you might be asked over stories like this. First of all, describe in words how the stored charge changes over time. Well, if you look at the growth factor, this is what's going to tell you how it's changing. Remember, the 200 kind of tells you where it's starting, but this is going to tell you how it changes. And so we know that as seconds pass, every time 1 second goes by, it's only going to have 90% remaining. So how would we describe that in words? Well, I think I just did. But maybe another way to describe it that's maybe a bit more common is, instead of saying there's 90% remaining every second, is to say that it's decreasing by 10% every second. So that's the way I would probably describe it. I would say that the stored charge is decreasing by 10% per second. That's probably the most common way to say it. And then you can use this formula as well to figure out what the quantity is that's remaining. What's the quantity remaining after either 20 seconds or 2 minutes? And I will let you do that, since that's a fairly low-level problem, and be ready to answer a quiz question on that. And then the second or the third question is to graph this, and of course that means you can type this in your calculator. And I hope that you would know that because it's a decreasing exponential function and it starts at 200, you can almost not even use your calculator to know at least what the sketch is going to be. It's going to start at 200 and it's going to decrease over time, and so it's going to be something like this. It's going to be an exponential function that goes down and heads toward the horizontal asymptote of the x-axis. So your question, though, is after you graph this and see a picture, we want to get it back into the story here. What does the horizontal asymptote of this graph tell us about this charge over time, the charge of the capacitor? And we need to kind of get that into words and have it make sense. That will be another question that you'll have to answer in the near future. Second example. Apparently there was a fine levied against the city of Yonkers, New York a few years ago. And the judge decided that their offense was so egregious that he would charge them $100. He would charge them $100 But then he would charge them double if they didn't pay it per day. So $100 doesn't sound too bad. A city can play that. But that fine will be $200 the next day, and $400 the next day, and $800 and $1,600. So it's going to double every day. The question is, when is that fine going to wipe out the entire budget, which is pretty big, $337 million? When will this fine reach $337 million? So your question is, when is this fine going to reach $337 million? And this is dollars too, just as a heads up. So it's going to start at $200. It's going to double every day. When will this hit $337 million? Well, I hope you're already in your mind thinking, oh, well, I've done something like that before. This is a increasing exponential function. It starts at 200, and it increases exponentially. Your question is, when is it going to hit $337 million? We just walked through one of those on our graphing calculators. You can do the same exact type of thing, but of course now you're dealing with a fairly large number up here. So you're going to have to you'll have to get a good window. You'll have to play with your window so that you can actually physically see this. And then your job will be to find the intersection point, and then whatever that value is right there, that's how many days it has taken for it to grow to $337 million. So you have the tools. I'd like you to walk through that and get that answer. You'll be answering that question in the near future as well. It'll look something like that. There's a picture of it. You just have to get the right window. All right, example 3, final example. Exponential decay is a common application of exponential functions in science and chemistry. And so if we started with a 500 microgram, I believe that's what that is, 500 microgram sample of carbon-14, and it decays down to 100. The question is, when will that happen? How long will it take? So here again is a formula, and you notice that since b is less than 0, that would indicate that it's a decreasing exponential function. So it's going to start at 500. This is just a sketch. It's going to start at 500. It's a decreasing exponential function. So they look like that. Our question is, when is it going to hit 100? 100 is going to be somewhere in this neck of the woods. And so your job is to figure out, when is it going to hit 100? And once again, we just learned a procedure using a calculator where you can graph a function that's an exponential and you can graph a function that's a horizontal line. And if you can find where those two meet, then you'll have your answer for t. So once again, you can complete that using your graphing calculator and using the intersect command under calculate. So that's it. There's a lot to there. There's a lot in there, a lot of notation and a lot of graphing calculator work. So your final assignment will be to see Canvas. I'll have the details there on what you're to do next. And as always, bring your questions, and I will see you in class.